student, we discussed there means atomic size or covalent radius. Covalent radius also known as atomic size here. So let us see here the order of covalent radius. So covalent radius increases down the group, but maybe some marginal change in atomic radius due to involvement of d and f orbitals electrons. It means when d and f orbital electrons are involved in inner core orbitals, so they have poor shielding effect and that affect the atomic size. So atomic size or covalent radius doesn't increase normally at a higher rate, but it increases slowly, means marginally changing from that, but the order is not going to be changed. So covalent radius order is like this: carbon, carbon, silicon, germanium, and stannic means tin, and this is lead. So this is the order of covalent radius. What is this? Is the order of covalent radius. So overall we will see here. So the effect of d and f orbitals is not so much in the case of covalent radius, and covalent radius increases down the group. Next is we see here ionization potential. Here second point is ionization potential. What is ionization potential? So it is also trained the ionization potential decreases down the group. You might be knowing decreases down the group. It decreases down the group and increases across the period here. It you have already discussed here. Okay, but here we will observe that there is a change in ionization potential due to involvement of d and f orbital after third cell onwards. Okay, so let us see here what things are affecting these. So this is the point that involvement of d and f orbital due to poor shielding, they are affecting the ionization potential. Due to poor shielding effect of d and f orbitals, they affect the size, and we can say it affects the ionization potential due to poor shielding effect or screening effect of it. So let us see what is the order of this. So let us see the order of ionization potential of 14 group elements is this. Let us see here. Order of this is like this: carbon, silicon, here carbon, silicon, then germanium, tin, and then lead. So I wrote this here. So let us see here how does it is changing, how does it changes it. So what is the order here? So let us see here what is the order. Carbon is more than the silicon, but silicon and ABC silicon and germanium. So in that case silicon is also more than the germanium. And next you see here germanium is more than the tin, but lead ionization potential is more. Means what is the order of increasing or decreasing order? This is the decreasing order of ionization potential. Means ionization potential of carbon is more than silicon, silicon is more than germanium, germanium is more than tin, but from tin to lead it increases. Just to see, here it is decreasing, here it is decreasing, but there it is increasing slightly or marginally. It increases slightly or marginally increases. So what you observe here, you observe that means little variation is observed in this case. From carbon to tin it decreases, but marginally increases from tin to lead. Okay students, so if we see this point, it is clear to everyone, whoever is watching here. Okay, let us see next point. So here if we see here electronegativity, our next is electronegativity. So we will see how does electronegativity change in the p block 14 group elements. So let us see here how does it vary. You might be knowing the size of 14 group is smaller than the 13 group. So there may be variation in their electronegativity, and normal trend of changing the electronegativity down the group, it decreases. Electronegativity decreases down the group, decreases and increases across the period. Here, this is the trend. But what is observed here due to intervening of d and f orbital is this. So let us see what is the order of this electronegativity. Carbon, electronegativity, silicon, and just sort of see here germanium, tin, and lead. Just sort of see here. So it is greater, means carbon is greater than silicon. Silicon and tin is lead, and germanium and tin is lead, and lead is more than that. It means the electronegativity of this group is carbon is more than silicon, and germanium and tin is lead. Germanium and tin is equal. Here you can see sign here, so we can observe here, and lead is more than the tin. So this is the trend, and these things are observed due to involvement of d and n f orbitals in a core cells. Okay, so let us say these are the properties. Let us move to physical properties. So let us see here physical properties. Physical property, we will see here what is the difference. All are solid, means carbon to tin are solid, but they have different physical properties. What in state they are same, but other properties they have different. So let us see what different properties they have. If we talk here about carbon and silicon, they are non-metal. Carbon and silicon are non-metal, while germanium is metalloid. Germanium is metalloid. And if we talk here tin and lead, so they are soft metal with low melting point. What are they? Are soft metal with low melting point. And if we talk normal way, if we compare this group physical property melting and boiling point with 13 groups, so they have higher melting and boiling point than the 13 groups. Here I have written here melting points and boiling points of this group is much higher than 13 group elements. So this is overall physical properties of this group elements. So student, let us see here. First property is oxidation states. Oxidation state and trend in chemical reactivity, means first chemical property is oxidation state and trend in chemical reactivity. So let us see how does the oxidation state vary, and it affects the properties of the elements. So here we are here to discuss this here. The common oxidation state is being shown by this group element is +4 and +2. What is +4 and +2? And in +4 oxidation state, they are covalent in nature. What is in +4 oxidation state? They are covalent in nature. What in +4 oxidation state? They are covalent in nature. The tendency to show +2 oxidation state increases down the group, means the tendency to show +2 oxidation states increases down the group here. Other points if we see here, means what different oxidation states are being shown by them. So let us see here. Maximum means carbon and silicon shows +4 oxidation state. Carbon and silicon shows +4 oxidation state. And before we discuss here, so the order of showing +2 oxidation state is increasing down the groups. Carbon and silicon shows +4, then germanium, then tin and then lead. And germanium also shows +4 and +2 oxidation state, but only it forms few compounds in +2 oxidation state. What is only form few compounds +2 oxidation states. If we see here, if we talk about here lead, here it also form compounds in +2 as well as in +4 oxidation state. But in this case, means in this case if we talk here, it acts as a strong reducing nature. It is in +2 state, it is strong reducing nature, means in +2 state it is reducing in nature. Okay, and here if we talk about lead, so it also shows +2 and +4 oxidation state, but it is most stable. It is most stable in +2 oxidation state, and in +4 oxidation state it acts as strong oxidizing agent. So how does it act as strong oxidizing agent? It has tendency to reduce. It has tendency to reduce itself, so it will act as strong oxidizing agents. Here other points we see here in tetravalent state, they are electron precise elements. They are electron precise elements means they have enough electron to write their bond structure and Lewis dot structure. They in tetravalent state they are electron precise. They are electron precise. It means they have enough electron to write their Lewis dot structure and bond structure. Okay, and because of this they do not act as Lewis acid or Lewis base. They do not behave as acid or base, means they do not behave as neither acid nor a base. Okay, Lewis base. And if we talk here in this, if we talk other very important point here, only in this group carbon is the element that shows only covalency 4. That shows only covalency 4. Rest of the elements show more than 4 valency because of availability of D and F orbitals. In carbon there is no D orbital, so it doesn't extend its valency more than 4. Rest of the elements can extend their valency and form the compound more than 4 coordination number. Okay students, so this is the point. And here if we talk here, so their highlights get hydrolyzed, means their highlight get hydrolyzed and they form complex. In the complexes their hybridization state change from sp3 to D2sp3. Okay, so this is overall oxidation state and trends in chemical world. I am writing here and explaining because it is taking less time. If I will explain together, it will be taking more time. So most of the topic can't be covered while doing this. So first I wrote here and I am explaining here. Okay students, next property is, next is reactivity towards oxidation, means 14 group elements have 4 electron in outermost shell and they form 2 type of oxide, MO and MO2. MO and MO2 type oxide they are formed. Okay, so let us see what is their nature and how does it vary down the group. So if we see here the MO and MO2 type of oxide here, yes, IO exists at a high temperature. It exists at only high temperature, and their acidic character, what is their acidic character, increases as the oxidation state increase. Like this, if we talk here, just sort of see here, if I am writing here SiO and SiO2, so oxidation state is therefore and here +2, so that is more acidic than this. What is that? That is more acidic than this. Means we have to remember here that SiO means monoxide is less acidic than the SiO2. What you got here? On increasing oxidation state, acidic character increases in 14 groups. If an element is forming same type of monoxide and dioxide, so which one is in higher oxidation forms more acidic oxides. Okay, and next point if you see here about this, oxides in higher oxidation states are more acidic. Oxides in higher oxidation states are more acidic. Here we have seen. If we talk here about the nature of the oxide, if they are forming MO and MO2 type of oxide. So let us see here students, here it is that CO2, SiO2, Ze2. CO2, SiO2, Ze2, these are acidic in nature. What is that? These are acidic in nature. You can see here, these are acidic in nature. Ooh, CO2, these are acidic in nature. And SnO2 and PbO2 are amphoteric in nature. You know that what are the amphoteric acid? Amphoteric acids are the acid which behave as acid as well as bases. Means they have dual behavior. Dual behavior, somewhere they behave as acid, at some places they behave as bases. So this is, and if you see here, if we talk here about monoxides, carbon monoxide is neutral. Carbon monoxide is neutral, and SiO and ZeO. These are very weak acid. Very weak acid, and Sn and Pb are amphoteric in nature. So these are overall the reactivity towards O2. What you observe here, they are forming 2 type of oxide, MO and MO2. So in MO, if we talk, there are acidic character increases on increasing the oxidation state of elements in oxides. That I have already told you here. So we can see here, and only few we talk here SiO2 exists at a high temperature only. SiO exists at a high temperature, and oxides in higher oxidation states are more acidic here, and we are talking here like this here acidic. Here if we talk like that, here we can see this one is less acidic than that. And next point, if we see here, if they are forming oxides, so what will be their nature and how does their properties or acidic nature change down the group. So let us see here in this, if we talk here CO2, SiO2 and G, these are acidic in nature, while SnO2 and PbO2 are amphoteric in nature. And other points we see here, monoxide CO is neutral, SiO and GO is very big acid, and SnO and PbO are amphoteric in nature. So these are the overall the properties, and this photo I will also add at the end of this lecture, so please watch this video till end. So let us see here, reactivity towards water means how does it react with water and what is the reactivity of these elements towards water. So what is observed in this case, it is observed that carbon, silicon and selenium do not react with water, means they don't have reactivity towards water. So here carbon, silicon and germanium do not react with water. Here carbon, silicon and germanium do not react with water. So what you observe here, you observe that what carbon, silicon and germanium do not react with water, while tin react with water and it decomposes the water into O2 and H2. What is that? Means these carbon, silicon and germanium do not react with water, but tin react with water and it decomposes into O2 and H2. Other points if we talk about lead, here it do not react with water due to formation of oxide on the surfaces. It forms oxide, protective oxide, and that prevent it from further reaction. What is that? Protective oxides are being formed by the lead to their surface and it prevent from further reactions. Okay students, this is there, means in that if we talk here carbon, silicon and germanium do not react with water and tin decomposes water into O2 and H2. Lead do not react with the water because of formation of protective surfaces, protective oxide on the surface, means it form lead oxide on that surface that prevent it from the further reactions. Okay students, next is reactivity towards halogens. Let us see reactivity towards halogens. So most of the elements of this group form MX2 and MX4 type of halide. Most of the elements of this group form MX2 and MX4 type of halide. Here if we see here, what is the other point here? Except carbon, other member directly combine with X2 to form MX2 and MX4 type of compound. Except carbon, other elements of this group directly combine with halogen to form MX2. So here MX2 means we can write here, just want to see here, it may be CCl4, SiCl4 and GCl4 like this also. It can be here, except just to see here, except carbon, other member directly combined with X2. Okay, and here if we talk here, about this. So carbon mostly less reactive towards this, and in general way we can say it forms means MX4 type of halide here. MX4 type of halides are mostly covalent in nature. What is their nature? They are covalent in nature. MX4 type of halides are covalent in nature. Like this, if we talk other property, if they are forming like this, I am taking here example, sp3 hybridization means in CCl4 hybridization state of C is sp3 and the structure is tetrahedral. But if we talk here in sp3 hybridization state, and in case of CCl4 means in tetrahedral maximum compounds are covalent in nature. But if we talk here, some exceptions are there. SnF4 and PbF4 are ionic in nature. What is that? Ionic in nature means in maximum compounds in MX4 are covalent in nature, but exception here, SnF4 or PbF4 are ionic in nature. If we talk here, SnI4 does not exist. SnI4 doesn't exist. Germanium and silicon form MX2. Just sort of see here, germanium and silicon forms only MX2 type of halide. MX2 type of halide means if we talk over general properties, so we can say it form MX2 and MX4 type of halide, but in that germanium and silicons only form MX2 type of halide here. And stability increases down the group. Their stability increases down the group here, like that. If we see GeCl2 is more stable than GeCl4. SnCl2 is more stable than SnCl4. Just sort of see here. What we observe here, we observe that means reactivity towards halogens. So what you observe here in this, if we talk that reactivity towards this, they form MX2 type of MX2 and MX4 type of halide. But only if we talk here, germanium and silicon. Germanium and silicons only form germanium and tin only form MX2 type of halide. Rest are forming MX4 type of halide. Like this, we can say Cl4, SiCl4, GeCl4. Except carbon, other elements directly combine with halogens and forming MX4 type of halide. In that, most of the halides are covalent in nature, and their hybridization state is sp3, and their structure is tetrahedral. And if we talk about here, in that most of the compounds are covalent in nature, but exception is that SnF4 and PbF4 are ionic in nature. And SnI4 does not exist here. In that, if we see here, germanium and silicon form MX2 type of halide, and stability of these MX2 type of halide is more than the MX4. Let us see example here. GeCl2 is more stable than GeCl4. SnCl2 is more stable than SnCl4, and their stability increases down the group. If we talk here, GeCl2 and SnCl2, so SnCl2 will be more stable than GeCl2. Then more stable. Got it? Okay, students, got it here. So next, if we see here, a bit of other points about this here. Let us see other points. What are the other points? Let us see here, students. So these are the points. What is the point? Let us see here. So this is the except CCl4, other halides easily hydrolyzed by water. Due to availability of d orbitals. Means due to availability of d orbital means other elements of this group are easily hydrolyzed due to availability of water. You might be knowing in carbon only electrons are present up to second shell, so d orbitals are not available there, while in others d orbitals are available, so d orbital can accept lone pair of electron of oxygen in d orbital, so they are easily hydrolyzed. Okay, so this is over all the properties, but let us see hydrolysis example by taking example of SiCl4. So let us see, students. The halides get hydrolyzed by water. So here we have taken here SiCl4 and it get hydrolyzed by water and forming SiOH whole 4 silicic acid. Okay, so this is overall p block elements of 14 group. In next